classes will be due on October 23rd. You will not be able to get this homework assignment graded before the second midterm, which will be on the October 25th. All right. Now, the materials will be covered. Okay, have something to share?
No, sorry.
Oh, okay, that's good, because my hearing is not that good. By the time I'm hearing that means it's pretty loud. All right, so if you guys want to have a thing, like sometimes I share stories with you guys, I would like to hear from you guys too. So don't just come by with a couple of you guys. You can raise your hand and share with the whole class, okay? All right, yes?
Well, technically what my story was, I went to Devil's Tower and Mount Rushmore last weekend, so that was fun.
Oh,
And I
okay.
turned 21 last night, so that was fun too.
Okay, is that what you're sharing with your friends?
Yeah, sorry, I don't mean to interrupt class.
Okay, no problem. All right, now should we have the, where am I? That's the whole point, I can't get disrupted, right? Because I don't remember what I just said. Now all I have is Mount Rushmore.
I mean, you were gonna mention something about the
Exam.
Oh, okay, yes, it is, the exam. All right, so we will have the exam 2, or maybe I'm thinking about my trip last time to California right now. Okay. All right, so the exam number 2 will take place on the 21st. I posted 3 sample tests. I have mentioned to you guys I've been teaching in classes for many years, so I might have a lot of papers circulating around, so why not just dump some of them to you guys, alright? But be careful though, because year to year, our 4th semester started at different time, so therefore our midterm material for different, I always do the same, we have 3 midterms, but the material will not be exactly in sync from year to year, right? Now, what will be covered for this midterm 2 will ended for today. So whatever it is will be all the way to today, right? We still have class on Friday, correct?
Yeah.
Should.
Yes.
I think so.
Yeah.
I got confused a little bit at the beginning of the semester when I made the syllabus, because last year when we had the midterm break, midterm something, it was a break.
Yeah, they just totally messed up the schedule this semester, and we started a whole week late, so we don't get a midterm break, and we have to come to class too. Now they changed it to the first 3 days before Thanksgiving. So
So
They basically shortened the break.
So,
Yeah.
so that means, let me get this right. So I put it onto break for Friday because according to last year, that was a break day, so we will have 3-day weekend. But that's no longer true anymore. It's a midterm break, means break, you're gonna come to PChem classes and having fun with me. So let's make it clear that clarification, because if you look at the schedule, I thought it was a midterm break, one-week break. And I agree with you, and the other thing is the Thanksgiving break, used to we have the whole week break, right, or some sort of break. But now we only have 3-day break or something.
they recently changed it to only Thursday and Friday off.
Only Thursday and Friday?
Yeah,
Yeah.
but personally, I already had travel planned, so I can't be there.
Where did you see that one?
They updated it on the 4th.
Oh, okay. Would you mind to pass that on to me? Not
Yeah.
now, but later. Oh, I look it up. Okay, anyway, let's get this straight. So I'll see you guys on Friday too. All right, so the material for the midterm 2 exam will cover all the way to today. Originally, I was thinking we would cover the 3-dimensional rotation, and I was like, no, I want to give you guys more time to prepare, so therefore only cover all the way to rotational on the plane. Okay, that's now. Because the first midterm mostly focused on some sort of math review, some sort of physics, and the foundation of the quantum mechanics. But the foundation of quantum mechanics is going to carry through the whole exam. So therefore, you want to review from the beginning all the way to rotational, 2-dimensional. Okay, all right. Okay, so we went through this. So the model for rotational on the plane is a rigid rotor. So what is the model? We have a free particle rotation, the particle with the mass m, and and 3 rotation on the xy plane, but with a fixed radius. And that's how we know we can generate a Hamiltonian operator. You know the variables for the wave function. It's a 2-dimensional rotation, but we fixed one of the variable r as a constant. That's why your wave function only carries one variable. So this is your solution for the wave function as well as the energy expression. Now, as we know, this rotation can be in different quantum states that are represented by your M sub L quantum number, which takes all integer values, all right? And this wave function has is a complex, in a complex form, okay? Because you have an I right there. Now, if you can see, there's a degeneracy beside the ground state when M sub L equal to 0. Other than that, the energy is to the power, proportional to the power of the M sub L squared. So therefore, plus minus makes no difference. So in that regard, we say this system is in the double degeneracy other than the ground state. All right, so in that regard, let's say I have M sub L, and the example plus minus 1, then your wave function equals to, of course, your constant, and then you have, if I write it out, when your M sub L equals plus minus 1, you have 2 wave functions. Maybe I should just split it out. So you have wave function corresponding to M sub L equal to 1, that equals to it carries one variable, it has a normalization constant. It's just an example. They all have the same energy. Now, what is the difference for the particle? If it's described by this quantum state versus this quantum state, they have the same energy. What is the differences?
Direction.
The difference is only in the rotational direction. Okay, one, the positive M sub L represent the rotation in the clockwise direction. The negative one is in the counterclockwise direction. All right, but they have the exact same energy because the rest are the same. All right, then we say, once we know the wave function expression, then we will be able to calculate, for instance, your observable in terms of angular momentum. Is the wave function for rotational motion an eigenfunction for angular momentum in the z component? Yes, we proved it last lecture. So the wave function for rotational motion is an eigenfunction. For the angular momentum in the z component, the operator. What is the eigenvalue? So it is. What is the value? What is the j value? Jz, actually, Jz, the z component is the only component the angular momentum this system has, so that also equal to the total angular momentum value. What is the value?
H bar ml.
It equals to M sub L H bar. We proved that, okay? Now, if the system is defined by this quantum state, say example, what would be the J value? right, H bar. Here S bar equals to,
Just H bar. Yeah, 1 times H bar.
right here. How about this one?
-1.
Yeah, be positive, that's about it. Alright, so therefore, the system has a quantized energy, also has a quantized angular momentum. And then we know the angular momentum position operator and follow the Heisenberg is an example of demonstration for the Heisenberg uncertainty operation. Alright, show you some examples of what it look like. This is only the real component, as you can see, for different ends of L, define a quantum state. And you guys can plot it if you wish. Because you know the ends of L value, you know the phi, which is 0 to 2 pi, you plug it into your calculator, fancy calculator, to show you what it looks like. Right? Alright, and I already went through with this with you. The both energy and angular momentum are quantized, and you can calculate the values at different quantum states. The one unique quantum state is the ground state. The ground state is when the energy has the minimum, which corresponding to x about equal to 0. That's when the system has the lowest energy. So that's your ground state. Okay. And then you can also calculate the angular momentum at the ground state is no rotational motion, so the energy is 0. Your angular momentum is also 0 value too. So therefore, there's a 0 point energy. There's a 0 angular momentum. Okay. Then we discuss about the significance in terms of plus minus sign for the wave function. That is really varies in the rotational orientation. Okay. All right. Now, have a sample problem, as usual. Alright, so can we evaluate the z component of the angular momentum and the kinetic energy of a particle on the ring that is described by this wave function? So I'm going to give you guys 2 or 3 minutes to think about this. And the kinetic energy for this particular particle rotation on the ring, and give you the exact wave function to define that quantum state. Right. So this is our solution for what? Rotational for a great particle rotation. With a fixed radius on the xy plane. So if you take a look at it, the wave function only carry one variable. That means the radius is fixed. And then it is an e function to the 2i phi. So it looks same as our solution for rigid rotor. Right? Because except this is a unnormalized wave function, cannot carry the normalization constant. Can you guys see this here? And specifically for this, the M sub L equivalent to equals. See this is, oh, okay, I can remove this because carries on. That's a general solution, right? So I M sub L phi. Now if you take a look at it, I phi, that's your M sub L. So the M sub L equals -2. Alright, now if you know this is a rigid rotor, and knowing the M sub L equals to 2, then we know the J, the Z component will equal the total, that equals to the angular momentum value is in general equal to M sub L H bar. Now we know M sub L equals -2 here, right, -2 h bar. All right, now how about the energy then? We know the energy expression for the particle rotation on the plane. I already wrote it here, so maybe I can just go back to this. Okay, that equals to at different quantum state proportional to the quantum number squared divided by 2I. Okay, I is the moment of inertia. All right, now the m sub L is -2 raised to the power of 2. That will be 4 h bar squared over 2m r squared. All right. So if you know the system, of course, you know the mass, you know the radius, so you can just represent right here. Now, unless I tell you what the mass, is, what the radius is, then you can go further. Otherwise, a solution like this is a generic solution. It's all good. Okay. Now, this is energy, which is the total energy for that rotational rigid rotor. Now, what is asking you for here? Yes.
Asking for kinetic energy? But
Yes. Asking for the kinetic energy. So how should we pursue it now? Yes.
you don't change it at all because.
It doesn't. So because the total energy is the sum of the what? Actually, you average because right now we're at the 1 state, so it's just the sum of the two components. The total energy always is the sum of the kinetic plus the potential energy. Now we know the total energy. Do we know the kinetic energy?
Yeah.
Yes. Why?
There's no potential energy.
Because this is a free particle rotation based on the model. Right? This is a solution. The solution for a free particle rotation. So therefore, you can directly infer the kinetic energy value as well. Any questions on this? So therefore, be familiar as you prepare for your exam. Familiar with all these postulates and think about what they are talking about, and then think about those three models. The free particle translational motion, the problem in the box. Think about what is a model. What is the Hamiltonian operator? What is the Schrödinger equation? What is the wave function solution? What is your energy solution? You know, once you know that, you can derive so many different things. You can still know the position, the momentum, all about it. And then you think about vibrational motion, right? For the vibrational motion, we started with a simple harmonic oscillator as a model, and then we extrapolate that discussion to diatomic molecules and understand the vibrational modes for diatomic molecules. And then you think about rotational motion for a free particle rotation on a two-dimensional system. And that's about it. All right. Any questions? Okay. All right. Then we will move on to before we move on to the rotation on the three-dimensional motion, I want to introduce something that is kind of cool. Is we discussed the rotational motion from the quantum mechanics point of view by starting with the generating Hamiltonian operator, plugging into the Schrödinger equation, and then solving for the wave function, and then derive the energy expression. But I want to show you, we actually can calculate the energy for that model without going through the quantum mechanics part. Okay, so how are we going to do this? All right, so we're looking at the model. I'm only talking about the energy perspective. So we actually can derive the energy expression just from the classic mechanics plus the Broglie relationship. We will reach to that expression as well. So basically, we can reach to the expression for the energy for this particular model from two perspectives, but they will give us the same value. All right, we show you from the quantum mechanics Now let me show you from the classic mechanics plus the de Broglie relation. Alright, so I wrote it on the slide. Okay, so if you think about from the classic mechanics, the energy, the total energy equal to the kinetic energy plus the potential energy. Since it's a free particle, then the potential energy is equal to 0. So the energy directly equal to the total energy equal to the energy of the kinetics. Now, the energy of the kinetics can be predicted and determined by the linear momentum squared divided by 2m. That's what you guys learned from physics, right? The kinetic energy equals p squared divided by 2m. All right. Now, because it's a rotational motion, there's a relationship between the angular momentum and the linear momentum. And their relationship equals to P times R. All right, now the plus minus is for the direction. Because using right-hand rule, they are 90 degrees, so therefore it's a cross product, and the angle between the linear momentum and angular momentum at the radius is 90 degrees, so therefore J equals the multiplication of the linear momentum times the radius. So therefore the P squared can be represented by the angular momentum J squared divided by R squared. Okay, then I can substitute the total energy expression with the angular momentum instead. So therefore, I'm getting the E equals J squared divided by 2mR squared. Okay, now we know mR squared is the moment of inertia, so I can substitute that. So therefore, J squared divided by 2I. Now, the first part of it is using the classical mechanics to derive the energy expression in terms of the angular momentum. Now we're going to bring in the de Broglie relation. So the de Broglie relation tells you the particle has both wave and particle property. Okay, so they're represented by the wavelength of the particle equals to the h divided by the linear momentum. So therefore, your linear momentum can be represented by h over lambda. All right, then you plug in the p here with the angular momentum component. So therefore, j equals plus minus hr over lambda. Now we know the wave function to be an acceptable wave function for the system, it has to be single valued. In that regard, the wave function has to be the same after you repeat one revolution. So therefore, the n lambda has to be equals to 2 pi r. All right, so what does that mean is, if you look at your particle rotates around this two-dimensional plane, you have a wave function corresponding around the edges of that plane, but they have to repeat after one revolution. So that is equivalent to as what we call the boundary condition. So therefore, the one revolution, are you guys still following me okay? At which part do you will which part do you feel you want me to? Do you have problem with the first part of the classic mechanics? That is fine, right? Okay, how about the quantization of the energy through the de Broglie relation? From that part? Okay, then we can start one here. So de Broglie relation tells you the particle and the wave property. All right, and then you know this side is 2RV. All right, because it's a rotational motion, so I'm going to represent the J in terms of the system in terms right? Nothing fancy. Because this is a de Broglie relationship. This is a through, the J is the plus minus T times R. Okay, now we're going to introduce alright. If the particle rotates on this two-dimensional plane with a fixed radius, right? What is the circumference? That's one. Isn't that one revolution? Yes. Okay, and the particle starting here, rotate, return to that one, keep rotating. So at any point, the successive rotation has to be reached to the same place, right? All right, so then the wavelength for that particle, or the integer number of the wavelength for that particle, it has to equal to what? Fits to the circumferences. Yes, that's, so it's a rotation. You rotate on this xy plane. You rotate around this, and then you can fit whatever the wavelength. The integer number of the wavelengths for that particle has to be equal to what? 2 pi r. Okay. In that case, then what you derive here is that the n has to be what? Equal to the integer number. We'll keep it going. And then what you have is you derive the lambda in terms of radius and the n, and then you plug in your lambda into this J expression. Right, and then you will derive your J value. Does it make sense? This is the nature of the system, and then you get the wavelengths in terms of 2 pi r n has to be integer number, and then this is your what we derive from the de Broglie plus the relationship between linear momentum and angular momentum. You plug in the lambda here, and then when you have it here, then you have r and r here, then you have h bar over 2 pi, h over 2 pi, which is h bar times n, but I also have what? Plus minus sign here. And then we can group the plus minus n using a different quantum number, that is your So from that, we derive the exact expression for the J value. Remember what is our J value from the quantum mechanics through the Schrödinger equation? Equal to the answer for R H bar. And that is exactly the same here. Okay. All right, and then once you know the value for the J, you can plug in back to the energy expression, and you will derive exactly the same as what you would from the quantum mechanics. So in that regard, the quantization for the rigid rotor, for the energy, we can obtain through this perspective, which do not need to solve in the Schrödinger equation. Just through the classic mechanics, brought in the de Broglie relationship, the wave-particle property, and then we will derive the expression. However, through this perspective, we will not be able to have the solution for the wave function. Right? Anyway, so I just want to show you that's another way we can derive the energy from two ways. Okay. Alright, but I'm not gonna test you guys on this one, so just want to show you. Okay, now let's move on. We have a rotational motion. I said I thought it's really fun to show you how we can derive the energy expression from a different perspective. But I'm not going to test you guys on the exam. Alright, now let's move on to the rotation on the sphere. Before I do that, I want to ask you guys a question. So let's say I have hydrogen atom. Alright, how many electrons in the hydrogen atom? Only one electron, right? What is the motion of the electron in the hydrogen atom?
Just all around it.
It's doing this, huh? It's doing this with a fixed radius. Oh, for sure, it's not fixed radius, right? So it has a motion of it around the
Electron cloud?
around the nucleus, isn't it? This is the nucleus and the electron right here orbits around your nucleus. Right? More specifically, we say this reside in a different atomic orbitals. What are they? The electron orbit around the nucleus. You can consider the nucleus as a stationary. Do not worry about that as an approximation. And then you have electron orbit around the nucleus. Yes. How many? What kind of orbitals are we talking about?
The 1s,
1s,
2s, 2p.
2s. Right. So you have different orbitals, which the 1s and 2s, they have the same shape, except what is the difference? What do we think of the s orbital shape?
Sphere.
Spherical.
Spherical? It is a spherical, huh? Alright, now what is the difference between 1s and 2s? Huh? It's a distance, right? Isn't it a distance on average? How the electron closer to the nucleus? Which one is closer?
S1.
Huh? C1s is closer. So what I was going to say for the particle rotation of the sphere is really leading for us to understand the electron motion in the atom. Right? Now, the electron motion in the atom, you will have vary your both on the sphere, on a different shape. You will vary your theta and the phi angle, but also vary your radius. Now, right now, we're going to do the particle rotation on the sphere. We want on the sphere, we want to take a step further, but also want to not get too crazy about it. So we're going to say the radius is still fixed. So if you think about this, a free particle rotation on the sphere, then from the quantum mechanics point of view, we need to generate our Hamiltonian operator. So that will be on the next model to understand the rotational motion. Instead of a two-dimensional plane, now bring to the three-dimensional system on the sphere. However, so if it's a sphere, then you will have x, y, z. 3 variables, because I only have one particle, so that will correspond to r, theta, and phi. So they from Cartesian coordinates to the spherical coordinates. Now we found the model. What do? We fix the radius as a constant. We did it. So then this reduced to reduce our variable from 3 variables to only how many? How many? 2. What are they? Theta and phi. Okay, so it is a 3-dimensional motion, but we hold one of the variables as a constant. So therefore, it only reduced to that wave function. It only depends on 2 variables right now. So therefore, if I want to write out the wave function for the rotation on the sphere with this model only contains 2 variables. Okay, now we know this already. Phi, define the angle between the phi is 2 pi. How about the theta? Is 0 to pi. One is the longitude, the other one is the latitude. Right. Then all clear? Okay. Now, before we dive in this, just review for you a little bit about the conversion between the Cartesian coordinates x, y, z to r, theta, and phi. Alrighty. So the x is equal to the r sine theta times cosine phi. Y equals to r sine theta times sine phi. The z equals to r cosine theta. So therefore, if you have a d phi, a volume, that's what we need to do because you can do a lot of integration. D phi equals to, for 3-dimensional system, is a dx times dy times dz due to the relationship between x, y, z versus r theta phi. If you want to integrate with respect to the r theta phi, what do you have? Okay, equals to r squared sine theta di d theta d phi. I just want you to, I know you guys are not going to do this, but I'm just going to point out to you, this does not directly equals to dr, d theta, and d phi. Instead, it's r squared this whole thing. Alright, alright. Now for the rotation of the sphere, it's easier for us to use the Cartesian coordinates. Okay, that's what we're going to do. Now, through the quantum mechanics approach, we need to come up let me breathe right there. What we're going to do, we have a model. We're going to generate our Hamiltonian operator. Then we plug into the Schrödinger equation. We're going to solve for it. It gives me a goosebump already because it's super complicated right now with this r theta phi right here. But we can go through it. Alright, now the Hamiltonian operator, right? It's an XYZ issue. Now that equals to the kinetic energy operator. It's a rotation on the sphere, it's 3 dimensions, then plus the potential energy operator. Now we know this is a free particle. It's a free particle rotation right away. This vanishes. Alright, so therefore what you only have as a free particle is the kinetic energy component. Okay, so the kinetic energy component, that's straightforward. It's a constant, h bar squared over its mass of the particle times 2, and then you have the derivative in all the axes. which is a three-dimensional rotation. So therefore, you will have the kinetic energy in both x, y, z component. So that is your Hamiltonian operator for the free particle rotation on the sphere. You write in terms of Cartesian coordinates. All right. Now, how about we switch to spherical coordinates? Okay. All right. I'm not going to ask you guys how we converted. You guys remember, but I'm still going to ask. Do you guys remember how to convert this with spherical coordinate? Here. Right. Now, just look at what do you guys call this? Can have a very easy symbol to represent these three components of the second order partial derivative in x, y, z. A symbol like this. That is the
Gradient,
what do we call that one?
the gradient square.
The del squared.
Oh, no, okay.
Is it a del squared? If it's not, then let me tell you, it is a del squared. So you can simplify this. Instead of write out all the components, you can just write out this as the equals to the del squared, which is the sum of the second order partial derivative with respect to x, y, z. Okay. Now this is not our question. Our question is, we want to use spherical coordinates. What would be the conversion between the Cartesian and spherical coordinates? All right. Now, this is a constant, so I do not really care right now. So what I'm care is a del squared, which will be converted into, with respect to the some review from us. It's really nothing fancy because you know the XYZ relationship versus theta phi. You can convert that one. All right, I'm not writing out the whole thing yet. I'm just writing out some portion of it. So this is a del squared, which is sum of these three second order derivative that equals to second order derivative with respect to the radius in general. And then you have the, did I write this? What did I write? Hey, I said I was checking, let you guys check with me. Nobody check with me? Alright, it doesn't look right. What did I miss here, guys? Huh? And that's why I need to have a slide, because I can't remember all of this. Alright, so if you convert it from the Cartesian coordinate to the spherical coordinates for the del squared, you have first term is the second order derivative with respect to your radius, then you carry 2 over r, then you have the first order partial with respect to your radius, then you carry the term related with the angles, which put it into this symbol. What do you guys call in your math for that symbol? You guys never exposed to that?
No.
Oh, that's hard. So you guys never exposed for that one? Then what you guys learn from the calculus 3?
Good question on that.
Vectors, or was that Chem 2?
No, Calc 3 is vectors.
Vectors.
Okay, then I have to say I'm so sorry that you missed a lot of beauty about that one. But that is called a Legendre, right there. See the? Alright, now that has a long relation with the related with the theta 5 angle component. Okay, this is not worried about right now. Right now I'm just saying the del squared is the sum of those three second order derivatives can be converted into the Cartesian coordinates related with the r, third part is your angle. Okay, let's worry about the angle later. Now, to our system, to our system, we can simplify this del squared. How can we simplify this? Well, what is our model? Our system is, what is it? A free particle rotation is a fixed radius. So therefore, how can we cancel it? I already told you we can cancel. So for our particle, let me make sure I write it right so that we don't think that square has no optimal. What do we have? This is not going to have it because its R is no longer a variable for our system. What else do we don't have? The second term too. The first two terms regarding with the radius will be vanished from our del squared. So our del squared, if I continue to write it here, will have the constant part 2n 1 over r squared, then this mathematic expression related with angle. It is all good? All good? Okay, now what is m times r squared? Moment of inertia. Okay, now let's come back to the Legendre expression. That equals to, guys, what is that equals to? 1 over sine squared, partial, second order partial derivative with respect to the phi angle, plus 1 over sine squared, partial over the theta, times sine theta, partial, oh, that is, let's see, I have 2 minutes. Let me write this one out because that is actually super important. Alright, so this guy equals to everything related with the angle group into this. The reason I want to write it out because to show you the operation sequence. Alright, so this is your operator right here. Now, if we take a look at it, it has 2 components. One is related with the partial derivative to the phi angle. The other one is to the theta angle. Okay? Right. Now, what do we see? We will have this, because this whole thing will operate on something. So the operation will be, this is, in that component, this is first. Then what you're going to have, multiply by sine theta. So ideally, you want to do this. The outcome of that, you take the partial derivative with respect to the theta angle. All right. Can't believe we only go through the Hamiltonian operator, but that's fine. We'll have Friday, right? Everybody's going to come back and we're going to